Okay, so in this video we're going to have a look at moving on from alkenes to addition polymerization, which involves alkenes. So it's still part of the alkenes topic in organic chemistry. So those compounds which we looked at in the last video, which had carbon-carbon double bonds. But we're going to have a look at how they're used to make in addition polymerization. So lots of you will know a little bit about polymerization. You'll probably associate polymers with plastics, so you're probably not far away in terms of what they are or how they're used in this context. So if I just tell you within our class notes, guys, you're starting here on page, so the class notes, you're starting on page 16 for polymers, and that runs through to page 20. So by the end of this, or shortly after the end of this, you should be able to have filled in all the gaps on page 16 through to 20. Okay, for the textbook reference, okay, you should be starting on page 20, same chapter as we've always been on, our chapter 12 of the organic textbook, or organic, but it's page 201, and that will bring you through to the end of polymers. There is halfway down page 206, so certainly worth reading that and doing the exercises and checking them, okay, from that perspective. Okay, so let's get started with our addition polymers. So this is when the double bond of an alkene molecule breaks, okay, and what happens then is that these little small alkene molecules all join together and they form a big long chain. And those big long massive chains, you're talking thousands upon thousands of these molecules joining together, okay, forms what we call the polymer. Okay, so it's called addition polymerization for the simple reason that you're just adding the molecules together. One adds to another, to another, to another, and so on and so forth. You end up with a huge molecules which have massive van der Waals forces, really massive, okay, and they end up with very high, large melting points, boiling points, hard materials that you would associate with polymers. Okay, now they are white whenever they're formed, but there's loads of ways the chemists have developed to dye these, so there's lots of them that can be coloured depending on what you want to use them for. Okay, so we're going to look first of all at the formation of polyethene. You all heard of polyethene used in plastic bags. Okay, primarily it's used in lots of things. Plastic water piping, loads and loads of things. Okay, so you take the name or the monomer that this comes from is ethene. So the monomer is the little molecule that you start off with. Okay, the polymer then is whenever all of those are joined together, and in this case they form polyethene. So this polymerization happens under specific conditions. You don't need to know too much about the conditions GCSE level. Okay, it's usually heat and catalysts. At A level you'd have to know the exact temperatures and the names of the catalysts involved. GCSE level that's not required, so you just need to know there's a little bit of heat and catalysts involved. So if we have a look at how these things join together. So this is the very start of the process. We take loads and loads of our ethene molecules. We'll take many millions of these. Okay, we've just a few on the screen obviously. And what happens is the heat in the catalyst, you can see, breaks the double bond and it turns it into a single bond. Now if you remember back to the very first video we did, maybe first or second, we said that carbon always had to have 4 bonds on it for it to be stable. Now if you look at all the carbons here after we've heated it in the catalyst, you'll see they only have 3 bonds. So they want to get another bond. Now how can they do that? Well, what they'll do is they'll pair up with another molecule, and that will continue to happen the whole way along, and this is where we get our chains made. And now if you notice that all of these monomers have linked together, you've got carbons which have got 4 bonds on them. And when you've got 4 bonds on them, they're stable. And the beauty of this process is they're stable now, but they've made these huge ongoing chains of polymers. Alright, and those are the plastics that we use in our plastic bags or PVC doors and windows and all sorts of things. Okay, so the general equation for this, you wouldn't have to write out this type of thing here. You wouldn't be expected to do that. So what you'll be asked maybe to write is just a small equation to represent what's happening. So N just is the number of ethenes that you'll start off with. That's a random number. It can be hundreds and thousands, millions even of those molecules. And then showing that the double bond is broken and that new bonds form either side of those carbons. Single bond in between them now. And then we have N number of those. Okay. Now this is called a repeating unit, which is an important term that you will need to be familiar with. So they'll ask you for a repeating unit of the monomer, and that's just the unit that continues on and on and on and on. Okay, so we're going to have a look at a video here of polythene manufacture. Okay, so
polyethene, usually called polythene, is an important thermoplastic material. The low-density form is used for a variety of purposes, including food and carrier bags. High-density polythene is used for bottles, buckets and pipes. Ethene, made from natural gas or crude oil, is taken into the plant and compressed. The gas is cooled and then passed to a reaction vessel where an initiator starts the polymerisation to form polythene. Unreacted ethene is separated and recycled to the compressor. The polymer is extruded and cut into pellets. On this site, ethene enters the plant by pipeline, and some is stored in this tank. The compressors are here, and these are the coolers. Polymerisation takes place in this building. The polymer is dried in this tower and stored here. Most of the ethene is produced in this cracking plant from naphtha and is carried by pipeline only a short distance to the polythene plant on the same site. Occasionally, ethene obtained from natural gas is used. Some ethene is stored in a stock tank to even out pressure fluctuations. The ethene is compressed to a pressure of 1500 atmospheres in 2 stages by these compressors. Compressing a gas heats it up, so the compressed ethene has to be cooled. Next to the compressors are rows of pipes in which the hot gas is cooled. Hot gas flows through the centre of the pipe. Cooling water flows in the opposite direction in the outer pipe. The compressed and cooled ethene in the red pipes is now a dense gas, almost like a liquid. Pumps add catalysts, called initiators, to the gas stream as it enters the reaction vessel. At 160 degrees Celsius and 1500 atmospheres pressure, polymerisation takes place in this vessel. Ethene gas is fed in at the top of the reaction vessel. Initiators are added. About 20% of the ethene is converted to polyethene at chain length about 5,000 ethene units. The mixture of polyethene and unreacted ethene is passed into the first of 2 separation vessels where unreacted ethene is removed and recycled. At this stage, additives such as antioxidants and stabilizers are added. The molten polythene is extruded into strings, which are cut into pellets and cooled by water. The pellets are carried into a decanter where most of the water is removed. They then pass into drying towers where, after being screened for size, water and any remaining ethene is removed using a stream of air. The pellets are stored to be packed in sacks for transport to users, where they'll be remelted and processed into finished products.
Okay, so that's just a sort of a glimpse into how the ethene is made.
Polyethene, usually called poly.
Okay, so uses of it, well, cling film bottles, always guys have a couple of these sort of at your disposal. They're not going to ask you 5 or 6, but make sure you've got a couple. And the properties of polythene that allows it to be used in this environment are that it is, of course, light. It is flexible. If you make it really thick, it's not particularly flexible, but for example, cling film and plastic bags are very thin. Okay, it's very unreactive, which is the beauty of nearly every polymer and plastic, is that they exist in the environment for a long time. So you can use them indoors and windows and water pipes outside, that sort of thing. The problem is that they then continue to exist in, if you put them into landfill, they certainly do not biodegrade, which is also a problem at the end of their useful life. Yeah, they are easily moulded and they can be coloured. You get lots of coloured doors, lots of coloured window frames, all made from polymers, which can be coloured into whatever the customer actually wants. Right, let's look at a second type then of polymer, polychloroethene, which is also on your syllabus that you need to know. This time the monomer, as you would imagine, is a little bit different. It's called chloroethene this time. Okay, still has a double bond, of course. You can see the ene in the name there. Some of you will probably be able to draw the structure of chloroethene without me putting it on the screen. So you maybe want to pause the video and have a go at that. And then okay, and the monomer then is the same. We have our monomer is chloroethane, and then our polymer is polychloroethene. So whenever you're naming polymers, guys, you just basically stick polymer at the start of the monomer's name. Right, so I'd like to think most of you were able to work out that chloroethene was 2 carbons, a double bond, and a chloro on there. So it doesn't matter if the chloro is here, or here, or here, or here, it doesn't matter. Again, to work out the structure of the repeating unit, break the double bond, okay, which we've done here, and then put new bonds coming out of the brackets either side. Remember to put your N there and your N down here. Okay, and that's PVC, that's polyvinyl chloride, is the common name given to that polymer. So I'm sure most of you have heard of polyvinyl chloride before. Uses of it, window frames, doors, gutterings, things like that. Okay, so again, guys, have a couple of those at your disposal. So if you are asked for them in an exam, you can set them out there. Okay, so I'm going to give you a couple of monomers here. I'm going to go through how to draw the repeating unit first of all, and then you guys can have a go at a couple and just check that you've got this cracked. Okay, so let's have a look here. Let's take something like, there's a few of these questions, guys, on in your notes, by the way, on page 17, which you can have a go at as well. Right, so let's take something like propane, which we met earlier in the course. So propane, we would draw it out. So the first thing I said is draw it out. The next thing that I would say is take the double bond to carbon. So these two here, we'll call them carbon X and carbon Y. And then take your groups that are attached to it and put them there, 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 and there. Now let's go and find those groups. Well, we know that here I have a hydrogen, so draw it in. Here I also have a hydrogen, so that is carbon X dealt with. Let's go to carbon Y. I have a hydrogen there. And here then on carbon Y, I have this, which is the CH3 group, so I do that. Okay, then I can draw my final monomer. So let's take carbon X and carbon Y, okay, and let's do our bonds again above and below, and we do our square brackets, and we remember now that our new bonds form there and there. That's the bond. They always form in the bonds that were X and Y that were in the double bond, and we put on our groups, so it's easy, H, 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 and I have CH3, and we might put our N in there, and reminder says that we have an N. It's number of repeating units there. Okay, so pretty straightforward. I'll do one more, okay, and then maybe you could go and do the ones on page 17 of your notes. So let's take but2ene, okay, another one that's on our syllabus. So we would draw it like so, double bond, hydrogen, put all our hydrogens in. You'll have to draw your hydrogens in an exam, guys. Don't be taking shortcuts like me here and just drawing the bonds. Okay, again, take our double bonds, X, we'll call them X and Y for those of you who need a little bit of clarity. Don't draw X and Y in an exam, by the way, that's just for me trying to explain it here. Now let's see, carbon X, I have a hydrogen there. And here I have a CH3. Okay, and carbon Y, I have hydrogen. And the other group attached to it is also CH3. Okay, take your two carbons which are in the double bond and break the double bond. I'll keep labeling them X and Y to make things easy for you. Okay, and then put your four groups back on again. So here we have hydrogen, hydrogen. I have a CH3 down here, CH3 down here. Put your bonds extending through the square brackets, or that should probably go to the carbon. Okay, and that is your repeating unit. So no matter what they give you, follow that process. The common mistake, the common wrong answer for this one would be people putting their new bonds, okay, putting a new bond here and here. That is completely wrong. It has to be on the carbons where the double bond. So you might get this type of answer from a student who wasn't quite sure what they're doing for this polymer repeating unit here, that sort of thing, with the four carbons here in a long chain, and that's just completely wrong. You can see here four carbons are like that, not in a long chain, and that's because the double bond is in the middle carbons. So I'm going to put a couple on here for you, and you can have a go at them. So I'll give you you could do but-1-ene, so maybe pause the video, okay, and see if you can work out the repeating unit for but-1-ene. Okay, so there's your X and Y this time. So your but-1-ene this time would be C2H5, which is that group that I have there. Hydrogen, 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 square brackets. Okay, doesn't matter whether the C2H5 is up there or down there. Okay, so that would be but-1-ene as opposed to butane on the last one. And then let's say I give you this structure here. Okay, again the repeating unit for that then would be, you can pause the video if you want. Okay, square brackets around it and just do that. That's my X and Y there. That's my X and Y there. N of those coming from N of those. Okay, so hopefully that clears that up and you can do your repeating units then. Okay, there's propane to polypropane, and there's sort of a general one actually, which is quite good. It's pretty much what I just spoken about. Okay, so you can see polymers have replaced lots of materials from days gone by. We've got paper and wood, been very much replaced by plastic bags nowadays, PVC doors, okay, last much longer, don't have to be painted, okay. So very resistant to chemicals, one thing and another, okay. So you've a variety of different types of plastics. Then you've got these what are called thermosetting plastics. Okay, very rigid plastics caused by this cross-linking of those chains, but unfortunately these can't be melted and reshaped, which makes it a bit difficult to recycle them, unfortunately. Okay, so, and you also have then thermoplastics, which are these ones, which can be melted and can be reshaped. They don't have these cross-links. So if you look at like the thermosetting plastic, you can see the black cross-links between all the polymer chains. That makes these really strong, really dense structures, but unfortunately when it comes to the end, you can only really burn them. They won't biodegrade and you can't recycle them. Okay, so the environmental problems associated with that, with plastics, okay, is that if you do burn them, they're very, very noxious. Okay, there is a huge economy behind plastics. Okay, but the main problem with them is, as you would probably imagine, is disposal of them. They simply have to go to landfill a lot of the times. They can try and burn them, but it's very difficult. They give off, even when you burn them, some very nasty, noxious fumes. Okay, and you can recycle some of them, but as I said, you can't recycle all of them, and they persist in landfill. They're non-biodegradable. Okay, so they persist in landfill for many, many years. Okay, microorganisms will not decompose them in landfill, and you can see, if you ever see photographs of landfill, lots and lots of plastic bags, and you'll hear about plastics in water causing damage to aquatic life as well. The other problem with them is that as they do slowly degrade in landfill, and when you burn them in incineration, they produce some very nasty gases. Lots of them contain fluorine and produce hydrogen fluoride. Lots of them, as you saw with the PVC, chlorine, produce hydrogen chloride. Very horrible gases. So that's just a little thing there about incineration, and it lists a few of the negatives, in that you produce carbon monoxide down here from them. It's toxic. Hydrogen cyanide is very toxic. Hydrogen chloride, sulfur dioxide, acidic gases. But the good thing about when you do burn them is you can use the heat from them to generate electricity. So there is positives from burning them, and there are, of course, negatives as well. All of those gases that are produced there would have to be produced in or kept within the incinerator. They're not allowed out to be pumped out into the atmosphere. Okay, and now there's a few comparison of some ways of advantages and disadvantages of getting rid of these things, and you'll see on your in your notes, guys, on page 20 that there's a little table, summary table. So you might want to stop the video and go across to page 20 and perhaps fill in that information on page 20 from the slide that I have on the board now, and make yourself aware of the advantages and disadvantages, of course, as well. Okay, right, now scientists and those of you who are inspired enough to go on into chemistry degrees and chemical engineering, biodegradable polymers are really hitting the market, and they have been on the market for a long time, but there's a huge amount of research going into them. And some of you probably have met these but don't even know you've met them. So I'll give you an example. Little plastics that you're washing up, tablets for your dishwasher and your washing machine go into. Okay, they are biodegradable plastics. In hospitals, they use laundry bags where they put very soiled, maybe and blood stained laundry into these plastic bags, which then go straight into the wash machine, and because they're biodegradable, the bag decomposes, so you don't have to take the soiled and blood stained laundry out of the plastic bag. Little stitches, those of you who have had stitches in time in the rugby pitch or hockey pitch or wherever. Okay, it used to be you had to go back to the nurse to get those stitches removed. Nowadays those just dissolve away because they're, again, biodegradable, and big research going into plastic bags and biodegradable plastic bags nowadays as well, for fairly obvious reasons, because they take up huge amounts of space in landfill. Okay guys, that should take you through in your notes now to the start of page 21, so you should be at the end of page 20, so make sure for your reference, if you've gone through, filled in all the gaps, and in terms of your textbook, that should bring you through now to sort of halfway down page 206 in your textbook. So again, make sure you've gone through that, read it, probably done some of the test yourself questions, and some of the other, there's lots of questions in there, guys, the show you can questions, and okay, do those and check them against the answers, please. Alright, so there you go, that is alkenes finished and polymers.